Hey guys, today we're going to look at lesson 9.1, logarithms and logarithmic functions. And we're going to start with task 1. Alright, so logarithms are something that you probably have never seen. Maybe you've heard of it before, but we haven't studied it in any of your math classes. So a logarithm is the inverse of an exponential equation, which you have studied. So let's look at logarithms. Alright, so it says to understand logarithmic functions as inverses of exponential functions. In the exponential function, f of x equals b to the x, the exponent is the independent variable. The power of the base b with any exponent is the dependent variable. For example, the output of f of x equals 2 to the x power are powers of 2 for all real exponent values. Since taking the inverse of a function reverses the input and outputs, the inverse of f of x equals 2 to the x takes powers of 2 as inputs and outputs exponents. The inverse of an exponential function is a logarithmic function. A logarithmic is the exponent to which a base must be raised to produce a given number. Alright, so a logarithmic function is written in the form f of x equals log base b of x, where b is not equal to 1 and greater than 0. And it's kind of hard to tell right here, but when I say log base b of x, this would be a subscript. You know how an exponent is a small number written above everything else? The base should be a small number written below everything else as a subscript. It's kind of hard to tell right here, but that's what it's supposed to be. All right, and the logarithm is it is read as the logarithm with base b of x, or log base b of x. All right, use the exponential function f of x equals 2 to the x to find values of its inverse. F inverse of x equals log base 2 of x. The log base 2 of x, and to draw the graph of f inverse of x. Alright, let's first start by creating a table of values for f of x equals 2 to the x power and drawing its graph. Alright, so they've already done this for you. So remember, x is your independent variable, so they chose values for x. And then when you plug these values in, you get the y value. The y value again is the f of x. Alright, so they've made a table of values, and then each ordered pair, each x and y value, can be graphed to sketch the curve. So this is the exponential graph of 2 to the x power. Alright, so it says, how does the table of f of x equals 2 to the x reveal that its inverse will be a function? Alright, so you know if it passes the vertical line test, that it is a function. But we know the inverse is the reflection over the y equals x. So it needs to pass like the horizontal test, I guess. So it says, how does the table reveal that its inverse will be a function? Oh, well, you can look at the table to tell that all the x values are unique and all the y values are unique. And the inverse means the outputs would become the inputs. So that's what it's talking about here. All right, so it says the values of the functions are always positive. Each value of the function is a real number. For each value of the function, there is only one corresponding value. So that would be the correct answer here because, again, to be a function, these have to be unique. When you switch it and make it the inverse, that means these have to be unique as well. So that's looking at the table. All right, how does the graph of f of x equal 2 to the x reveal that its inverse will be a function? All right, so if you look at the graph, it passes the horizontal line test. Remember, the vertical line test tells you if a graph is a function or not. This says, will the inverse be a function? So that means you have to look at the horizontal line test. All right, do you need to restrict the domain of f of x equals 2 to the x for its inverse to be a function? What characteristics of f of x equals 2 to the x allows you to make this conclusion? All right, so it says, yes, since the values of the range are greater than 0, the domain needs to be restricted. All right, so the domain is not restricted here, so we can input any x's. So I'm going to say no, the domain does not have to be restricted. So let's see, out of these two choices, what's the best one? So no, since f of x equals 2 to the x is always increasing. It's exponential growth. Remember, when the base is greater than 1, this is exponential growth. So it's always increasing. There will never be different domain values that correspond to the same range value. So that sounds true to me. So let's see what this one says. No, since the domain of f of x equals 2 to the x is not restricted, the domain will not need to be restricted for the inverse to be a function. The domain will not need to be. All right, so this is the one that's the best answer because it talks about the domain values corresponding with the range values. So I'm going to say the middle one is the best answer. All right, C part says, how does the symmetry of a graph and its inverse help you predict the appearance of the graph of f inverse of x equals log base b of 2? All right, so the symmetry, remember that anytime you're looking at an inverse, it's the reflection of the y equal x. So let's see what they say. The graph of the logarithmic function will be the reflection of the graph of the exponential function across the y equal x. So that sounds exactly right to me. This one says y equals negative x, so that's not right. The graph will be a reflection across the x-axis, no, y-axis, no. So the only one that makes sense is the first one there. So it's always going to be, the inverse will always be a reflection across the y equal x. How does this relate to the isotopes? While the exponential function has blank as an isotope, the log function. Okay, so remember the exponential function, it grows exponentially like this, and it has an isotope on the x-axis. Well, the logarithmic function, being the inverse, is going to have an isotope at the y-axis. All right, how can you use the values in the table for f of x to find ordered pairs that satisfy f inverse of x equals log base 2 of x? All right, how can you use the values in the table to find ordered pairs that satisfy? Well, all you have to do is switch the x and the y. Remember, when you have an ordered pair, if you switch the x and the y, then that is the inverse. So this says use the domain values, use the range values, reverse the domain and range. So that's the best answer. Use the first domain value with the last. No, you don't want to switch up the ordered pairs. You just reverse the x and y. All right, it says, what are the resulting ordered pairs? All right, if you look back at the table, all right, the table for the exponential function goes from negative 2 to 3, and it starts with 0.25 to 8. So the inverse will be 0.25, comma, negative 2, 0.5, comma, negative 1, etc. So the only one that could be is the first one. So you just switch the x and y, and that's the inverse. All right, add the points you identified in part D to the graph. Draw a smooth curve through your points. All right, 0.25 and negative 2. All right, so this is 1.25. Negative 2 would be about right here. Well, I don't know why my graph moved. Now it's not letting me erase it. All right, for some reason my graph is not working, so let's look at the graph here. All right, we already looked at 2 to the x power. That's my exponential function. And now we're trying to look at the inverse function. So let's look at the logarithmic function. All right, so if it's log base 2, I can't use any of these buttons. I'll show you later more how to use the log buttons. I don't know if mine has the newest version. All right, in my calculator here, if I go to Math and I scroll down to log base, I can enter any base. You're going to learn later that these are for special circumstances, so you can't just use the log button here because it says log. But you can come here and do log base, and then it allows me to put the base 2 in here, and then to the x power. And then you can see that that is a reflection across the y equal x line. So again, this was the exponential function. This is the logarithmic function. So you can see the exponential function has that isotope is the x-axis. And you can see that the inverse here comes up along the y-axis. It kind of looks like it's hard to see down through here. It's getting very, very, very close to the y-axis, but it's not actually going to touch it. So that isotope there is the y-axis, which we looked at before. And I don't know why my graph is not letting me graph there. All right, it says, does the graph confirm your answer to parts A through C? So A through C, we reverse the x's and y's. And yes, it does confirm all of that. So it says, find the average rate of change for f of x over the successive intervals. All right, remember your average rate of change is your difference of y's over your difference of x's. So you're going to go back to the ordered pair, and because we're running out of time, I'm going to pause the video to do this. So you're going to take -2 to -1. So you're going to do your difference of y's divided by your difference of x's, and you're going to do it for each interval that it asks for. When you finish this, just unpause the video and continue. All right, so here's the average rate of change that I got. And you can see that again, you just do the difference of y's between these x's and do that for each interval that it gave us. All right, then it says find the average rate of change for f inverse of x. Okay, so f inverse of x means you're going to switch your x and y's. So it's going to be just the opposite. So if you look down here, it's going to be 4, 2, 1, 0.5, and 0.25. And I know that without even working it out, because I know that if I switch my x's and y's, that's also going to switch my average rate of change. All right, it says, what do you observe? Well, it's exactly the opposite because we switched our x's and y's. So where this goes from 0.25 down to 4, this one goes from 4 down to 0.25. All right, so that's a little bit about logarithmic functions, and we will continue in task 2. If you have any questions, let me know.